So this lesson is lesson 10 on ridge regression. Today we're going to talk about the mathematics that's involved, and this is for students who've had multivariable calculus and understand Lagrange multiplier or Lagrange multipliers. And we're going to overfit some data, and we're going to use ridge regression, some regularization, if you will, in order to fix our problem. So that's the idea for today's lesson. So again, if you're in this class, and I think I've agreed upon, if you haven't got a partner yet, I need to know who your partner is for the project, and I'm not opposed to having three-person groups, I should say. So just send me an email or something to let me know who your partner is. So there's a couple things that I want to get out. Okay, so let's go to an example. So what I'm going to show you is a regularization on a model, and I'm going to on purpose overfit this model. So let's see. This is in CoCalc, so I've delivered this to all you guys in CoCalc, so you can pull this up. And what this represents here, let me just print this out. What this represents is maybe the size of a house, 2,000 square foot house, and maybe it went for 150,000, or it's worth 150,000, or maybe that's what it sold for last time. And then the 2,200 square foot house sold for 153,000, and so on and so forth, right? So I want a model that could basically, I could put a different size house in, and it would possibly give me sort of, an estimate for it. So knowing that there's only 5 points in this data, I can definitely create a fourth order, so I asked this in class, but a fourth order polynomial that will definitely go through all 5 of these points. And so that's the purpose of this, right? So I can do that, and the way that I'm going to do it is just taking this data frame, and I'm going to add on the S2, which is the size squared, the S3, which is the size cubed, and S4, which is the fourth. I'm going to add those suckers on there. I don't think I need the predictor thing, so I'm going to take that out, and then let's just see what the so this is using the linear algebra in order to get us the coefficients, and you'll see that 7.52, and so here 7.52 is your beta 0, and then this negative 1.2, it's not 7.52, it's like 75, so 1, 2, 3, 4, 75,272, and this will be negative 124.848, and then this will have some decimal places in it, and so on and so forth. So if you use these coefficients, beta 0, beta 1, beta 2, beta 3, beta 4, right, and then did x times beta, you get y hat, right? So what is y hat? Well, it's pretty dang close to the actual values. So if you go up here, 150 is what we expect for the first one, and 150 is what you get for the first one, basically, out to machine precision, 153 and 190, and so on and so forth, right? So you can see that we just created a model, overfitted it on purpose, so that it would go through every single one of these points, right? So that's what we got. So let's calculate r squared for this thing, and just to show you how good, obviously, how good this model is going to be, if we just use this one statistic and didn't worry about any of the other things that are kind of going along. So let's go y hat. Oh, I need to come down. So y underscore hat is equal to x times beta. So I just shown that. So x times beta. Same thing we did right here. So that's going to give us y hat. And then if I want SSE, I'm just going to simply go y minus y hat squared, and then sum it. And then SST will equal y, oops, I need 2 of them, y minus y dot mean. So this is an example of broadcasting. Y dot mean is one number. And so what has to happen is Python takes this y, which will be price. It'll be this vector here, and it knows that it's got a length of 5. So I may make this y mean 5 big so that I can do the subtraction. So someone was asking me about broadcasting earlier today, and I was just giving you an example of it's actually doing that there. And then R2 is equal to 1 minus SSE over SST, and then we can print R2. We get up to machine precision sort of R squared, right? 0.9999. And if you saw this, hopefully you're kind of thinking in your head, I might have overfit the data. And if you had a validation set, you could definitely figure out that you did. All right, so I'm just going to create, so this is just more of some Python stuff. If I wanted to create a column that did that, it would just be X times B. Yeah, shift enter, and you can kind of see what the model's producing, and they're exactly the same. And then this is our validation set. So our validation set contains 2,100, 2,800 square feet, and then 500. Now, 500 probably you don't want to use it because it's outside your predictor values, like it's way up here. But I just wanted to show you how awful it is. So how awful this model is. So we got x1 is this NumPy array, and so note that what we did here is we had a 1 for the column of 1s. So that's going to be multiplied by the beta 0. And then the 2,100, 2,800, and 500 is the x value, right? So that's the thing that goes in then x squared, and then x cubed, and then x to the 4th. So we need all of these things and all of these numbers in the matrix in order for it to work out, in order for my matrix multiplication to work out. So I'm going to call this y new. It's going to be equal to x1 matrix multiply times beta. All right, so think about what that's doing. It's taking that row times the column of betas, and it's going to give you what it's predicting for y new. And then I'm just going to print them out. So I'm going to say x1 comma y1 in. Remember what zip does? It puts two lists together, or two NumPy arrays together. X1 comma y new. And then, so we're going to print an f string. So print, use an f string here. And then the variable on the left. So x1. Now I've got to pull out the 1th. So what it's doing is it's getting out this entire row here, and then it'll go get that entire row and that entire. I don't want the entire row to print out here. And even if you did, this is not how you would do it. You can't print a list or a NumPy array vector in this using an f string. So I had to pull out the 1th one, right? So 0, 1. So it's going to put out 2,100, 2,800, and 500. And then I don't know, tell it how many spaces we want to. I don't know, 6 maybe. We'll see if that's right. And then I'm going to pull out y1. Yeah, y1. The 0th one of those. And then let's see, that's going to be I don't know, 12.3f. Remember what the 12 is, the number of spaces. This is the number of decimals, and then f is that's a floating point number. Shift enter, and we see that 2,100. So you kind of look here and go, well, does this make sense? Do we expect to get something like this? Again, the validation data would have what the real price values were in there, but we're just looking at the predictions right now, and we would not expect 2,100 to be in 20. We'd expect it to be somewhere close to 150 to 153, and the fact that it's 140 is kind of unnerving a little bit. And then 2,800, like, so if you go in here, look at 2,800, you see it should be between 175 and 198. Should, I mean, it doesn't have to be. It could be like 172 or something, but 154 is, again, that's a little off. So you might suspect that maybe there's something wrong with this model. And then finally, if you see 500, now again, that's outside of our predictor values. However, I mean, I should not expect $29,646,000 house at 500. It just doesn't make any sense. So again, another indicator that something's kind of going wrong. Now what I want to do is real quick, just graph it, just show you kind of what's going on. So let me do this lambda function. So lambda x, again, some of this stuff I'm just doing to educate you on some of the Python things that you can do. I'm going to create a vector, so 1x, x squared, x to the 3rd. And then I'm going to matrix multiply that by b, the current b that we have, whatever we solved for up there. Again, we're not passing it in. We're not passing in a b here. We're just using the global variable beta, or b, I should say. And then I just want to go for x1 in x. What do we want to do? I want to y underscore x. That's my list, this blank list that I have up here, and I'm going to append it. I'm going to append f of x1 into there. And then we're just going to simply plot it. So I want to plot my x versus y underscore x. Whatever that's going to be, I think it's going to be a curve. And then I'm going to use a scatter plot from the Seaborn library. So SNS dot, it's not just scatter plot. Data is equal to df x eyes, and y is the price. All right, so we get a scatter plot, and then make sure you show it so it doesn't get some weird thing. So of course, PLT, what did I do? Just plot, oh, PLT.plot. All right, so I don't like that. I don't like the fact that it's red too. So I'm gonna let the scatter plot be blue. So I'm gonna say color equals blue, and I'm gonna let the marker. I can change the marker here too. I'm gonna let it be a capital X. That doesn't like that. Oh, it's equal to. All right, so you can kind of see what's going on there, right? So you can see that that's the first point, the second point, the third point, the fourth, and the fifth, and that the fact that the model is going through each one of those points. It shouldn't surprise you that 2100, right? So if I chose a number here, I chose one that is going to be way down. It doesn't make a lot of sense probably. These probably would with the numbers in between here. So if I would have chosen a number between 2200 and whatever this one is, 2500, then it probably would have made a lot, maybe it probably would have made a lot more sense. And then, but obviously these don't, right? So the ones down here, 2800 is probably not great. Again, I chose these numbers because I knew what this graph looked like. All right, so the idea here is like, maybe I don't know which one of these variables should be squeezed out or decreased, but I know that this is not a good model. So I'm going to do something. I'm going to use regularization to find new parameters. That's the idea with this lesson. So let's go back, let's jump back over. So our model's overfitting the data. We got a high R squared. We got low on the validation set. We need to shrink the coefficients of the model. So let's look and see what the mathematics is behind this. The two most important ones are, I shouldn't say most important, the two most common are ridge regression. So this is what we're gonna do today for the most part, because the squared term on the penalty function lends itself to calculus. And then this one is an absolute value. So they're very related, but they both involve these penalty functions. So let me write out what so I'm gonna just type in or write in here ridge regression. So you guys are not in class right now, but I'm going to sort of let it be like we are sitting in class. And then I'm going to write out the function. So J ridge is some function of beta that has, well, we're going to start off with the 2 over n. So we've done this before. We've done this loss function before. I equals 1 to n of, let's see, let's let this be yi hat. It really doesn't matter which one. And then yi squared, right? So that, I claim we've done that one before. And then I'm going to add a penalty. So I'm going to add some lambda times beta 1 squared, beta 2 squared, beta p squared. So we're going to do that. And let me name this, right? So I'm going to name this one something that we've already seen in this class. I'm going to call this J. This SL stands for squared loss. So this is the squared loss function that we've already seen. And we know how to calculate that using linear algebra. We've seen that. Go back and check it out if you don't remember. This new one here, I'm going to call it G of beta. Right? So again, there's a reason why I'm doing this, why I'm kind of setting these apart here, and hopefully we'll see here in a second. But just to be clear, I want to do this. This is the objective of this thing. I want to minimize this beta that's a member of p plus 1 dimensional space. Why is it p plus 1? Well, there's p parameters here, but don't notice that there's no beta 0. So I'm not penalizing the beta 0. The beta 0 is going to be whatever it is. But there is a beta 0 over here, right? So remember what this is. This y hat is beta 0 plus beta 1 x1 plus beta 2 x2 plus beta p xp, right? So remember, there are betas running around in here, and oh, by the way, it's in p plus 1 dimensional space. So I'm gonna optimize this entire function here, this J ridge of beta. So I'm going to find the beta that basically minimizes that function. Okay, so let's roll down just a second. I'm going to come up just so I can kind of see what this thing looks like, because right now I don't know if I'll be able to kind of show what this thing looks like, but this reformulation. So I'm going to reformulate this thing, or another formulation. So another formulation is this. So if you ever had nonlinear optimization, usually we start from the formulation I'm about to write, and then we go to this one because this is usually an easier one to, find the partial derivative, set them equal to 0. But in this case, I want to go backwards basically. And so I'm going to say it's really this is the minimization that we want to do. Again, we're finding the beta. It's a member of p plus 1 dimensional space. But I'm going to find it for the squared loss function. Right, this blue one right here, subject to some constraint. And the one constraint that I'm going to put in is this guy, which is beta 1 squared plus beta 2 squared, plus beta p squared is less than or equal to s. And the way this thing's done is I'm going to go ahead and let this set it equal to s. So this will be my reformulation of this thing. So that's our new kind of thing that we want to do, right? So I'm just going to put this in a big giant box, and I'm going to recall 3 things about multivariable calculus that you might want to remember. So we're going to use Lagrange multipliers. And the fact in these 3 facts. If you understand these 3 facts, or if you remember these 3 facts, then I think you'll understand kind of what's going on here, right? So you got to remember what level curves are. Because we're the military academy, I'm going to write in contour lines, right, on a map, right? So if you're on a map and you're looking at contour lines, that's the same thing as looking at level curves. How do you get these? So if I had a function of x and y, then the way that you get a contour or a level curve is you just set it equal to the curve that you're interested in. Set it equal to some value z, I don't know, 100. So if you have this function and you set it equal to 100, well, then you can then graph it on a 2-dimensional case, right? So and that becomes the level curve for 100. And then you can then you can put another number in at 200, then 300, and 400, or whatever it is, and then you can take that, solve for it, and then sort of see what the picture is. In other words, if my function is, and it's kind of similar to one here, x squared plus y squared, if we set it equal to 100, then we have a radius of 10, right? So this is, and then you'd label this 100. And then I would set in, I don't know, what's another one that's easy? 400, right? So if I put in the 400 level curve, actually it'd be twice as far. So this one would have a radius of 10, the next one would have a radius of 20, and that would be the 400 level curve, and so on and so forth. So that's, just don't forget how to do that, how you actually find level curves. The second thing I will review is really the relationship. So the relationship between a level curve and the gradient. Now, if we were just learning what a gradient was in a level curve, I would spend some time and show you how to do this, but I'm assuming that everybody in here has had multivariable calculus, and you guys went through that whole discussion and the fact that they're orthogonal, right? So if I'm on this level curve here, let me choose another color. If I'm here, then, and this is 100 or 400, then I know my gradient is pointing in that direction, orthogonal to that level curve. If I was over here, it would be the same way. It would be orthogonal to the level curve, right? They're not pointing in the same direction. It just depends on where you're at. Is where, and why is it pointing that way as opposed to that way? Because this is also orthogonal to that curve. Is the fact that the gradient always points in the direction of max increase. Here, let me control Z a couple. That sucker on there, and then I want to erase that. And then I want to make this more orthogonal, right? So this would be the negative gradient. This one would be the positive gradient. Why? Because this one's pointing towards going lower, and this one's pointing to go towards going higher. Again, the relationship between level curve and the gradient is an important thing to understand. Is if you're going to visualize some of these things that we talked about. And the last one is scalar multiplication. Scalar multiplication. And the idea behind that is to simply get, if I gave you this vector v, what I want you to realize is we can shoot. Let me go. If I multiply this thing by a scalar, it's either going to make it shorter so I'll call this lambda v. If lambda is between 0 and 1, then it's going to be shorter than the actual v. If it's greater than 1, then it's going to be some lambda v is going to be, again, pointing in the same direction but a little bit longer. And then the last one is if I'm here, I can point in the other way if it's negative, right? So this is obviously a negative, some number less than 1, absolute value less than 1. So just remember that, and the fact that how can I make this true? So 1, 2 we know is not equal to 2, 4, but there is a lambda that I can put and do scalar multiplication, like if lambda is equal to 1/2, then this would be true. It wouldn't be true if this were the case. If I erased, well, I won't erase, I'll just rewrite. If it was 1, 3, there is no lambda such that this is true. Because these are on the same line, if you will, then there is a scalar multiplication that will make these equal. The fact that this points in a different direction than this guy, well, then there is no lambda that can do that. So that's the idea behind the scalar multiplications. Just understand that if they are sort of pointing in the same direction or even opposite directions, then I can choose some lambda. All right, so let's draw in. Let me draw. Oh no, I want the other shape. I want this one. So I'm going to draw in a little bit of this thing, right? So the first thing I'm going to put in is the one constraint, the beta. So I'm going to let this be beta 1, let this be beta 2, and then I'm going to draw in this constraint here as, and again, that's not a perfect circle, but whatever S is, I guess it would be S squared S. It'd be square root of S, right? So that would be a radius of square root of S. And then we have some let's see, objective. So this might be, and we've seen this before where I put the loss function. So I'm putting the square loss function out here. And then eventually, if you kept doing this enough, you would get to a point where, oops, you're going to get to a point where this thing will just touch that, right? So there is a level curve out there that I can choose. It's going to just touch that thing right there. And because I know this is a minimum of the way this thing's designed, so let me see if I can put this in here. So I don't want to be in erase mode. This will be my min. And if that's the min, well, which way does the gradient point for this guy? It points in that direction, right? So it's orthogonal. And it's orthogonal to that one level curve that comes in there. And then, well, if we're talking about this function here and this constraint, oh, I forgot to explain this. This constraint, this guy right here, is exactly how you find a level curve. So the fact that I drew this on here, this is one level curve of this function g of b. So this is one level curve of g of b equals to s, right? And then, so where does it point? Well, we know that there's a minimum for this function at 0, 0, 0, 0, right? So I know that's the minimum, so its function points in that direction. So now I have two gradients that are on the same line, so therefore I can do this. I can just say, well, the gradient of JSL, I guess I could write this in the color that we're talking about. So this is JSL. And so I can now write that. Let me put this in blue, pen mode. So I'm going to say the gradient of J is equal to negative, right? Because I wanted to point in the opposite direction. The negative of the gradient, we'll put that, negative of gradient G. All right, so the point here is this is not correct right now. It's close, because I want these to point in the same direction. So that's why I'm multiplying by a negative. But the thing that we got to remember is this idea of scalar multiplication, right? Because here, 1, 2 is not equal. If this lambda wasn't here, it wouldn't be equal to 2, 4. But with this lambda here, there is a lambda that I can choose to make these equal. And that's the point, right? I don't know what the gradient is for this function. It depends on what the x values are. I don't know what the x and the y values are. I don't know what the gradient is for this one. I guess I don't know what the betas are. So again, I don't know what that is either. But I know at the point where we're interested in this guy right here, that these will be orthogonal, or I'm sorry, one will be pointing one direction, one will be pointing another direction on the same line, and therefore we can do this where we can have them as a scalar multiple of each other. Okay, so that's all I got to really say about that. And then note what's happening here. So this was the optimal, right? This was the minimum. This was the point that you found without using any kind of, without adding this penalty. And now what we're doing is we're moving it down to here, right? So that would actually be my beta 1 and beta 0. So don't forget kind of what we're doing here in this overall minimization is that's what we would have been finding had this not been here. But now that that's there, well, that's moving us down to in this direction. All right. So I forgot to put SL on here. So this should be SL, right? So this is the square loss function. This guy. All right, we should know, so come back up. We already know, we've already done this JSL. That's equal to X transpose X beta. If you don't remember this, go back to your notes. Well, I think lesson 4 or something we did this. But this is and we did this several times throughout the, I don't know, lesson 4 through like 5 or 6. We did this several times in order to find that gradient. This will give you that gradient. Oh, we can't forget to divide by 2n. Matter of fact, I'm going to write it like this, divided by 2n. And then the next thing is I got to calculate, so I got to calculate this gradient here. So what is that guy equal to? It's the partial of g with respect to beta 0, the partial of g with respect to beta 1, and so on and so forth, all the way to we get the partial of g with respect to beta p. So that is the vector that we're looking for. And oh, by the way, we know what g is. We know g is just these square pieces here. So I can just calculate those. It's pretty straightforward. This first one, there is no beta 0 in this one. That's the one that we're not trying to penalize. So we know the partial is equal to 0. The partial of this one would be 2 beta 1, 2 beta 2, ... all the way till we get to 2 beta p. So again, p plus 1 dimensional vector here. And I'm going to put these two things in with this guy, this little sucker right. I'm going to put all of this stuff together, and let's see what we come up with. So I'm going to bring this lambda times, oops, I forgot my grade, my vector symbol. I'm going to bring all this over to the other side. So I got X transpose X beta minus Y, let's see, plus lambda, and I'm going to bring the 2 out. So there's a 2 in each one of these, and 2 times 0 is 0. So I can bring the 2 out, and then I'm going to call this beta minus. Why is it beta minus? Because it should be beta, right? It should be this beta vector, but it's missing this 0 here, right? So I want this beta minus, so beta minus to equal everything except for, it's basically equal to beta, except for I got a 0 here for beta 0. So that's why I just don't want to forget that. And that's equal to the 0 vector. So this is going to be a vector, right? That's that gradient that we talked about for SL. Oh, I forgot to divide by 2n. Okay, so this is, I want to solve for beta now. So I'm going to multiply through by 2n. 2n times that would be 4n lambda. So I got X transpose X beta minus Y plus 4n lambda beta minus, can't forget that. And then if I take 2n and multiply by 0, I still get the 0 vector. Now bring this X transpose in, you get X transpose X beta minus X transpose Y plus 4n lambda beta minus is equal to 0. And we can take this to the other side and then take a beta out, right? So let's go X transpose X plus 4n lambda. And I'm going to leave a little space here for something. And then I'm going to multiply that by beta. I'm going to actually bring in a real beta out. And then that is equal to, so bring this over, you get X transpose Y. So the problem here is this is a scalar, and I need some matrix here because X transpose X is always going to be a matrix, given the fact that X is a matrix. So X transpose X will be a matrix. It'll be a however many X transpose row columns. So it'll be however many columns that's in this in X, right? It'll be column by column. All right, so X transpose Y. So the problem here is how do you pull out beta? So if I were to put this back in, it wouldn't be right? Because I would need a beta, a negative here. And oh, by the way, we can't even like add these together because this is a scalar and this is a matrix. So I got to add something here in order that if I multiply by beta, I will get this beta minus. So if this were just beta, so if this guy were just beta, the correct thing would be I. So I'd be identity. The identity times beta gives me beta, and we'd be money. But it's not that easy, right? Because I got this extra 0 in there. So the deal is I'm going to call this thing E, and it's almost the identity matrix. So, but the only thing missing is this first one, right? So matter of fact, I'm just going to put the identity. I'm going to start off with the identity, and then 0, 1, 0, dot, 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 0. 0, 0, 1, dot, 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 0, right? So there's a whole bunch of zeros in here after that. And then dot, 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 dot. So this would be a 0, 0, 0, dot, dot, dot. And then this last one would be a 1, right? So an identity is the one that has the ones on the diagonal and then zeros everywhere else. And so the only difference is I'm going to call this E. I'm going to take out this first one so that if I multiply by beta 0, beta 1, beta P, I get exactly what I want here. I want this beta minus, which we know, like if you take this and multiply by this, you get a 0. If you take this and multiply by this, you get beta 1, and so on and so forth. So we get exactly what we want in there. So that's why that sucker right there is E. All right. At this point, I would take any questions, but apparently, you guys are video doing this, so don't worry about it. But now I can solve for beta, right? So I know that beta is equal to X transpose X plus 4n lambda E inverse, and then times X transpose Y. And there you have it. And let's knock it out. All right, so let's use this in order to solve our problem that we're interested in. So let's take this guy, and if I can remember what that looks like, I'm going to take a picture of it. That didn't work at all. Hold on, let me hit new. New turns it, take a picture of it, so I can bring it over here if I need it. And now I'm going to go to Python, and we're going to use those parameters in order to do what we need it to do. So I'm going to let lambda equal to 100. There is no perfect solution for lambda, so I'm going to let lambda equal to 100. I'm going to let n equal to the length of my data frame, right? That's how many data points that we have. I'm going to let p be the already bad, so I'm going to let it be the length of the already bad beta that we have. I'm going to let E equal to, remember what E was? It was that identity matrix, so np.I, and then I'm going to let it be P by P. And then E of 0, 0 equals 0. All right, so I just took the first element of the first row, so the first row, first column, and turned it into a 0 instead of the 1. And now I can use it. So B is equal to np.linear algebra dot inverse of x dot transpose time matrix multiplied x, and then plus 4 times n times lambda. Recall I got to use LAM for lambda instead of lambda. I can't spell it out because it's a keyword, and Python will tell you how dumb you are if you try to do that. And then E would be that matrix, and I'm doing not a matrix multiply because this is a scalar. I'm doing this so that it does the broadcasting stuff, turns into a matrix so that we can simply multiply it actually it's a bicomponent multiply by times E. And then matrix multiply x dot transpose, and then matrix multiply times y. And then I'm going to put this in parentheses just because I'm used to doing that. I don't think you need it, but let's just see what happens. And then print B. We get things that are a little bit smaller. And now, so this is also in CodeCalc. This is the reproduction of what we did above. I just want to see what this thing looks like and the scatter plot on it. And you can see that now things have changed. And if I use this model that we just created on that other data, you'll see that 2100 will be something, maybe a little bit bigger than this one. But again, it's not something out of the ordinary. Okay. Well, that's really all I got for this lesson. I mean, we're going to use the scikit-learn version of this next time, so be okay with that and understand that before you are able to push the button on scikit-learn, the objective here is for you to understand kind of where this stuff's coming from and be able to use it. Oh, last thing, I know I had a little bit of time. Lasso. So what's the difference in this and lasso? Is lasso does the absolute value. So this G function here would be the absolute value of beta 1 plus the absolute value of beta 2, and this would be my constraint. It's less than or equal to S, or equal to S if we're going to get this last one. And then what happens is the constraint looks like this little diamond. And as this function gets bigger and bigger and bigger, it's going to end up intersecting this guy before it does any of the other ones, right? So in general, lasso will zero out some of these betas that are not needed, as opposed to Ridge, which just make them really, really small. And okay, well, that's all I got, guys. Hopefully you got something out of this one. We will see you next time.